This meeting is being recorded.
Okay, from our previous class, we discussed about what is a VLAN, how does it separate a big broadcast domain into smaller broadcast domains. We discussed about access port and trunk port, and we have seen communication between two devices inside the same VLAN, but we have seen on the same switch versus having two different switches by connecting via trunk port. Any questions on the previous class, guys?
No, sir.
No, sir.
Okay, today we will jump on to a different topic called spanning tree. Let's talk about spanning tree, what it is, what is the use of spanning tree, and how it helps us. And we'll also talk about the flavors of spanning tree. What are the features that are improved on the spanning tree by introducing different flavors in the spanning tree. Okay, so today we'll talk about spanning tree protocol. Okay, so spanning tree is a network protocol which is used to prevent layer 2 loops in the network. Basically, when we have a loop in the network, when we have redundant links, that might cause a broadcast storm. So to avoid the loop-free topology, spanning tree will be helping us to provide that. So let's take a topology that might show us the broadcast storm, and how does the spanning tree will avoid it, we will see here in a second now. So I'm going to take this as example topology. So I have switch 1, switch 2, and switch 3. Switch 1 is connected to switch 2, and switch 1 is connected to switch 3, and there is a connection between switch 2 to switch 3. So if you observe, there is a loop in the network. For example, a PC is connected here. So this MAC address learned by the switch 2 will be sent to switch 1, and the PC switch 2 will also send the same MAC address to the switch 3. Now switch 3 will send that to the switch 1 will send it to the switch 3. Now switch 3 got the same MAC address from two different places. One is from switch 2 and the other one is from switch 1. And switch 3 will send the same MAC address to switch 1. And switch 1 will again send that MAC to switch 2. And so on and so forth. There is a big loop in the network. So when there is a continuous loop in the network, that will cause the MAC address table to flood, because the same MAC address is looping from, if you look at the MAC address table of switch 3, that MAC address will be learning from this port. Let's say this is port 1 and also this port via port 2. So it will learn the MAC address from port 1, and also it will loop and learn it via switch 2 as well, because switch 2 will be sending to switch 1 and switch 1 will be sending to switch 3. So the same MAC address is looping on port 1 and port 2. So there is a continuous flapping that is happening between the ports. So this will eventually get your network down. Your switch 1, switch 2, and switch 3 all will go down, because there is a lot of overhead. So when the resources are being extremely used, switch cannot handle the traffic and it will die. Eventually the switch will go down. So to avoid this condition, whenever there is First of all, we don't want loops in the network. But for some reason, if we did something like this, we wanted to have an automatic mechanism to avoid the loop without any manual configuration. So if an engineer does a mistake like this by connecting a loop network, we want the spanning tree to come into the picture and then avoid the loops in the network. So when we have a loop in the network like this, we wanted to make sure that spanning tree will come into the picture, will be handy for us, and it will avoid the loop for us. So spanning tree is used to avoid the loop. So let's see how it does it. So now we understood how the loop forms. Now let's see how the spanning tree will rescue us in avoiding this loop. Okay. Okay, so when the switch 1, 2, 3 are connected in this fashion, switch 1 will send a message to switch 2, and switch 1 will send a message to switch 3, so on and so forth. Switch 2 will send a message to switch 3, and switch 2 will send a message to switch 1. They all exchange messages which are called as BPDUs. BPDU. BPDU full form is Bridge Protocol Data Unit. BPDUs are nothing but the messages that are exchanged between the switches. As soon as we connect the switches in this fashion, they all will have the messages exchanged between them, and they exchange the priorities between them. So let's say the switch 2 priority is 4096, switch 3 priority is 2048, and switch 1 priority is 1024. I took as an example here. So they all exchange the priorities. Okay, so switch 1 will send its priority number to the switch 2, and switch 2 will send its priority number to the switch 1. Okay, like that, switch 1 will send the priority number to the switch 3, and switch 3 will send the priority number to the switch 1. Switch 2 will send its priority number to the switch 3, and switch 3 will send its priority number to the switch 2. So they all exchange the priorities. So whichever switch that has the lowest priority, that becomes the root bridge. So out of all the switches, whichever switch has the lowest priority, that becomes the root bridge. So what is root bridge means? A root bridge will always have the ports in the forwarding state. It will never block a port to avoid the loop. So in our example, because this became the root bridge, it will put this port in the forwarding state and this put in the forwarding state. Okay, so this port is not blocked and this port is not blocked. So now the next lowest priority is 2048. So now 2048 is the secondary best switch in the network. So this will also not block the port because this is a second priority, right? So this one will put in the forwarding state and this one put in the forwarding state. Now we have switch 2 with the highest priority. That means it considered as the least considered switch as the root bridge. So because of the highest priority, this one will not be used. So now we have either this port or this port to be blocked. Okay, so let me erase few things. Okay. So we have either this port to be blocked or this port to be blocked. But because this port is closest to the root bridge, this port is directly connected to the root bridge, this port will not be blocked. And the remaining port is this one. So this port will be blocked. So the topology, even though there is like a loop topology, after the root bridge, this one will look like this. So you have a root switch or root bridge. You have one of the non-root bridge and other non-root bridge. So you have this port connected and this port connected, and you will have this port blocked. So there is no connection between these switches. So this avoids the loop between the switches. So this port is blocked. So only this is the topology that we're gonna see. This port is blocked in the network. So when we have a loop in the network, spanning tree will elect the root bridge. Whichever is the lowest priority, that becomes the root bridge. And the switches with the highest priority in the network will have to block one of the port, and that port is whichever is close to the root bridge, that port will not be blocked. So now I have only the option of having this port to be blocked. That is how it will avoid the root bridge. That is how it will avoid the loop in the network. Any questions?
Yes, sir. What do you mean by priority? Based on what means it get the priority?
We as an engineer can define the priority.
Okay.
Priority is the value that we can define, so that we wanted to make which switch to be root, which switch not to be root, that we can decide as an engineer.
Okay.
Sir, with the highest switch priority, we are blocking the one which is nearer to the root bridge, right? So
No,
we are not blocking.
we are not blocking the one nearer to the root bridge. We are blocking the one which is away from the root bridge, not near to the root bridge.
So if the information is passing from switch 3, where we have like lesser priority, then will that information will be passed to switch 2 if the way is blocked?
No, it will have to go through only switch 1 and go to switch 2.
Okay, sir.
If switch 3, something connected to here, wants to talk to something over here, it has to pass through switch 1 and then go to switch 2 and then reach here. It cannot directly talk between them because this port is blocked.
After the process, can we disable the blocking, sir?
No, we cannot, because if you disable the spanning tree, you are creating a loop in the network.
Okay.
But what if this switch go down, right? What if this switch go down? If this switch go down, there is no loop at all. This one link go down, this one link go down, and there is only one link between them, right?
Yeah.
Then there is no point of root bridge spanning tree at all. Whenever there is a loop, then only to avoid that loop, spanning tree will come into the picture.
Okay, sir. Thank you.
Okay, what if the priorities are all same? Let's say the priority here is 32768, 32768, 32768. What if all the priorities are same? If all the priorities are same, there is the concept of MAC address, right? Every switch has its own MAC address. Like we defined, MAC address is the default value that is provided by the vendor that is hard-coded by the switch to the switch, right? So whichever switch has the lowest MAC address, that becomes the root bridge. For example, this one is all like all A's. This one is all B's. This one is all C's. So here in this case, this one is the lowest bridge ID, lowest MAC address. So this becomes the root bridge. So this port will be in the forwarding state. This port will be in the forwarding state. So out of B and C, this is the lowest priority. So now this port will be in the forwarding state and this port will be in the forwarding state. So this is the one which is the highest MAC address. So it can either block this one or this one. But because this port is closest to the root bridge, this one will be in the forwarding state and this port will be blocked. Okay. So if the priorities are all matching, whichever switch has the lowest MAC address, that becomes the root bridge. So the formula is priority bridge ID equal to priority plus MAC address. Okay, if all the priorities are matching, then whichever has the lowest MAC address, that will define the bridge ID. Bridge ID is nothing but this value that we are calling it as priority, right? I mean, it's a combination of priority that is defined on the switch plus MAC address. So if you don't create any priority, you will see the priority as 32768 as a default value on the switch itself. That is a default spanning tree priority that is defined on the switch. Okay. Any questions, guys?
No, sir.
Okay. So now there is a problem here because before we talk about the problem, there are states in which this switches has to pass through to elect as a root bridge. There are different states that the switch has to pass through, and there are different port states that are. So now let's talk about the port states in the switch. Okay, so I'm gonna delete this one. So now let's look at the port states. Okay. Okay. Okay, so the first state is, well, discarded state. Okay, so here in this case, that means that it is not even listening on the spanning tree at all, or disabled state. You can call discarded or disabled state, both are same. So listening, learning, forwarding, blocking. So these are the 5 states of the spanning tree. So now let's see what does these states mean. Okay, so now I have switch 1, switch 2, switch 3. Now I have a combination. Okay, so now we know that switches will exchange the priorities, and whichever has the lowest priority, that becomes the root bridge. We know this process already. Now there are different states in which it does forwarding or blocking. So initially, when the spanning tree, like this one, will have a priority. So for ease of understanding, I'm going to take the same priorities: 1024, 2048, 4096. Okay, so I took priorities on the switches: 1024, 2048, and 4096 as the priorities on each switch. Now, before this switch sending the priority to this one, this switch sending to the priority to that one, likewise between them, these ports will be in the disabled or discarded state, meaning the spanning tree did not even started sending the BPDU messages. That state is called discarded or disabled state. So at that moment of time, switches didn't even start sending the BPDU messages. Okay. So next step is listening state. In the listening state, this switch will start sending its BPDU message and it waits for the other BPDU to receive. Okay, so in the listening state, this switch will send the BPDU, and this switch will send the BPDU, and this switch will send the BPDU. They all will send the BPDUs, but they wait for the other BPDU to receive on their side. So this switch will wait for the BPDUs from this side, and this switch will wait from the BPDU from this side. So listening is where it will start sending the BPDUs, but it waits for the neighbors to send the BPDU back. So the learning state is where this switch will receive the BPDU from the other side, this switch will receive the BPDU from the other side, and this switch will receive the BPDU from the other side. So listening is where it sends the BPDU to the other side, but the learning is where it receives the BPDU from the other switch. Okay, and forwarding is means, so this switch will know the priority of this switch and this switch. Now it knows this as the root bridge, right? So forwarding is where it knows that it has to put in the forwarding state. So they all agree on putting, okay, now I know the root bridges, I'll put my ports in the forwarding state. And blocking state is where that is the last switch that is putting its port in the blocking state. In this case, this port is blocked because the highest priority. So whatever we discussed in our previous slide, these are the stages it has to go through to decide which port has to be forwarded, which port have to be blocked. For that, it has to go through these 5 stages. Discarded or disabled state where the spanning tree is not turned on or did not initiate the message yet. Listening is where it initiated the message and it waits for the response. Learning is where it gets the response like a BPDU message. It learns the priority from the other switch. And then forwarding is where it puts the port in the forwarding state, and the blocking is where the non-root bridge will put the port in the blocking state. These are the 5 states of the spanning tree. Any questions?
Sir, can you
No,
briefly explain this one to one? I mean, just briefly explain how this tree will help for in real time. Just little bit confused.
Spanning tree will avoid the loop in the network. When there is a loop in the network, instead of going your switches to go down, it will avoid the loop in the network. That is the use case. If you have a loop, then what is the point of sending the data? Just forget about the spanning tree. Let's take a user is here. He's trying to go to a destination. He has one path to go. Okay, and he's trying to go to, let's say he's in Austin, Texas, and he wants to go to Chicago. Okay, so he has one road he can go, but at the same time, let's say there is a loop in the road. He keeps on, the message is, he keeps on roaming on that loop and he never goes to the destination. Then what's the point of he sending the data when it's keep on looping here and there? He has to go to the actual destination. Similarly, if a PC is connected here and if its PC is connected here, if they keep on looping between them, how does it even reach there? Are you getting my point now?
Yes, sir, I'm getting about the 5 stages.
Stages are the transition path to elect what is the root bridge. If you understand the election process, these are the steps it has to go through to get either a root bridge in forwarding state or discarding state.
Okay, the stages involved in that. Thank you, sir. I get it.
Sir, so these loops are like man-made errors, or they somehow form after forming this network?
If you connect a network in a loop topology, it could be a man-made error, or it could be a redundant path that you wanted to apply in your network. Meaning, think about an example like this. Okay, so you have a switch 1, switch 2, You have one link here, one link here. You created a loop in the network. Okay, you created a loop between these two switches, but there is a reason behind this loop. Why means you have a PC1 here connected to the switch, and you have a PC2 here connected to the switch. So let's write down PC1 and PC2. Okay, so this is switch 1 and this is switch 2. Okay, so you connected like this. Okay, you thought that if this link go down, I have a redundant path to go to this PC. Your intention was not to rely on a single link. If this link go down, you have an alternative path, right? So this is not an error. This is like you being cautious that if one link go down, if one interface go down, I have another interface to go as the path. But you created a loop here. Are you getting my point?
Yes, sir.
So if you ask me, is this an error? Absolutely not. You're being cautious and you connected two links between two switches to make sure that if one link go down, you have another link for the traffic to flow. But without knowingly, you created a loop in the network that your MAC address being looping between these two ports. Right?
Yeah.
So spanning tree will rescue your thought. What it will do, it will put one port in the blocking state. It will block one of the port. As soon as this link go down, it will bring this link up from blocking state to forwarding state.
Okay. So the spanning tree comes into the picture only when the MAC address table is flooded, right, sir?
Exactly.
Or,
when there is
okay.
loop, yes. Whenever there is a loop, spanning tree will avoid the loop by electing the root bridge.
Okay, sir.
If
Got
you
you.
have only switch 1 and switch 2 and just one link, then there is no spanning tree here. What is the need of spanning tree, right?
Yeah, yeah. Got you, sir. Yeah. Thank you.
Okay, so now we talked about why do we need spanning tree, what is the use case of spanning tree, and what are the steps that are involved, transition states that are involved to form the root bridge. Now we will talk about the port types in the spanning tree. Okay, same thing. I took the similar topology as an example. I have taken 1024, 2048, and 4096 as the spanning tree priorities. So now we have to look into the port roles, right? So we have to talk about root port, designated port, alternate port, or block port. Okay, so whichever, in this case, who is the root bridge?
Switch 1.
1Z.
Which
Oh, yeah.
one?
Yeah, which one is the root bridge? So the ports whichever on the root bridge. So this one and this one, these are called designated ports. DP and DP. Okay. So the ports whichever are close to the root bridge. So this is the root bridge, right? So the ports whichever are close to the root bridge. So this port is close and this port is close. So this port and this port are called root ports. Okay. So the ports on the root bridge are called designated ports. I'm getting some echo noise. Can you please mute? So the ports which are closest to the root bridge are called root ports. So this one is a root port and this one is a root port. Now we have this port which should be blocked, right? So this one has the highest priority. So this one will be called as blocked port and this one will be called as alternate port. Okay. So here the port on the root bridge, the port on the non-root bridge, which is supposed to be blocked, is called blocked port. And the port on the non-root bridge, which is opposite to the blocked port, is called alternate port. So these are the port types that we define to understand what is a root bridge port and what is a non-root bridge port. So when we define the ports that are on the root bridge are called designated ports. The ports which are close to the root bridge are called root ports. And the link on which the ports will be blocked are called blocked ports. And the adjacent side of the blocked port is called an alternate port. These are the port types. Okay. So this is the concept of different port types in the spanning tree. Any questions?
No, sir.
Okay. So now we understood spanning tree is used to avoid the loop in the network. But if you see, most of the people think that why should I block a port? Am I not having issue like taking an, if I wanted to reach something here, why should I go from here to here and then go here? Why should this port should always be blocked? That is an obvious question, right? If I have a path between these two, why should the spanning tree should be blocking my port? Why should it not be forwarded, right? Even though there is a loop, there should be a mechanism, right? So that's a common question that bothers everyone. So that's why they improved the spanning tree by doing per VLAN spanning tree. So instead of blocking the entire port level, they did something that is at a VLAN level. So now let's see what if there are two VLANs that we configure on the switch, and then we will define what is a per VLAN spanning tree is. So VLAN spanning tree is the one which we discussed now is common spanning tree, which is the original spanning tree. Okay, it's the first edition of spanning tree. So they improved that. They did a flavor to it, which is called per VLAN spanning tree. Give me 1 second, I'll be right back. 1 second. Okay, I'm back. So we had issue with the spanning tree, right? We don't want port to be always blocked. We should get an alternative to have some sort of mechanism to allow the traffic on that port. So that's why they came up with the per VLAN spanning tree. So now let's take the similar example. Same topology. Let's say there are two VLANs on this this switch port. Okay, so let's say this PC is in VLAN 10 and this PC is in VLAN 20. Okay, this is VLAN 10 access port VLAN 20 and this is access port VLAN 10. Okay, so what we do is, instead of doing the priority at the switch level, we define the priority at the VLAN level. Okay, so for VLAN 10 we will make this priority as, so let's do one thing. VLAN 10 priority is 4096. VLAN 10 priority is 2048. VLAN 10 1024. Okay, for VLAN 20, priority is 4096. VLAN 20 priority is 1024. VLAN 20 priority is 2048. Okay, so if you observe, the priority is changed at the VLAN level, not at the switch level. So the root bridge for VLAN 10 will be this one. This one will be the root bridge because it has the priority of 1024. This is VLAN 10. Okay, so VLAN 10 priority is 1024. So for VLAN 10, this one will be forwarding state, this one will be in the forwarding state, but for VLAN 10, this is 4096. So this port will be blocked state. But if you observe for VLAN 20, this becomes the root bridge. So this one will be in the forwarding state, this one will be in the forwarding state. But for VLAN 20, this is the lowest priority. So this will be blocked. So we are not blocking the port at the switch level, but for the VLAN level, we are altering the condition of allowing the traffic of one link over the other. If you observe for VLAN 10, the traffic flows like this. That is how the VLAN 10 traffic looks like. If you observe the VLAN 20 traffic, yeah, that is how it looks like. If you observe the logical topology for VLAN 10, it looks like this. That is the logical topology of VLAN 10. If you observe the logical topology of VLAN 20, that is the logical topology of VLAN 20. So we are not completely blocking one link. We are using both the links, but depend on the priority or at the VLAN level, we are choosing one link over the other for the path to go. This way, we are not completely shutting down the link. Okay. Any questions?
So with the VLAN 20, we got like 4096 as a highest priority, right? So within the switch 2 and switch 3, we have as the lowest priority bridge as VLAN 20. And with the switch 3, we have like 2048 as third switch, right? So why the loop is taking, why we need to block the opposite bridge, right? Loop which is opposite to the root bridge, we need to block it. But why we are blocking at switch 1?
Are you talking about VLAN 20, right?
Yes, sir.
Okay, so let's do one thing. Let's have one more diagram. Okay, so we have so this is our switch condition, right? So this is our topology at the beginning, and we have VLAN 20 priority as 1024. This is VLAN 20 priority of 2048. And this is VLAN 20 priority of 4096. So this is the root bridge. Do you agree?
Yes.
So this port will be in the forwarding state and this port will be in the forwarding state. Now, the port whichever is the closest to the root bridge is called root port. This one is root port, which is in the forwarding state. And this is the root port, which is in the forwarding state. Correct? Do you agree?
Yes, sir.
Now we have only one link. Now tell me which port, which side will be blocked?
Switch 2.
The one which has highest priority number.
So this
Opposite
port
to
will
the
be
root
blocked.
bridge.
This port will be blocked. This port will be allowed. Correct?
Yes.
That's what I have done. If I remove this link, this is same as this one.
Okay.
Any questions?
Sir, does this spanning tree allow the switch to see whether it's going through VLAN 10 or VLAN 20?
Yes, you can see that what VLAN is acting as the root bridge and what is not. You can see with the show commands on the switch. Yes. Okay. So there is a problem here with this setup as well. There is a problem. That problem is when you have hundreds and hundreds of VLANs. For every VLAN, the switch has to calculate the root bridge, non-root bridge, forwarding port, blocking port. It adds a lot of computational overhead on the switch. The CPU will be more and more used to, let's say that if you have like 100 VLANs, so to calculate 100 root bridges, 100 non-root bridges, it's a lot of computational power. Do you guys agree? It is a lot of confusion, right?
Yes, sir.
So that is why they came up with the next feature of spanning tree, which is called as multi-spanning tree. Okay.
Yes, sir.
So now the flavor is multi-spanning tree. So what they'll do is Same thing. So let's say you have 100 VLANs. Okay, so VLAN 1, VLAN 2, so on and so forth. You have 100 VLANs. So instead of doing per VLAN spanning tree, what they will do is they will make them into groups. Okay, so group 1, VLAN 1 to VLAN, let's say 25. Group 2, VLAN 2 to VLAN 26 to VLAN 50. Group 3, VLAN 51 to VLAN 75. Group 4, VLAN 76 to VLAN 100. So we are separating 100 VLANs into 4 groups. So we will define the priority at the group level, not at the VLAN level. So for group 1, this can become the root bridge. So this port will be in the forwarding state, and this port will be in the forwarding state, and this can be in the blocked state. For group 2, this can be the root bridge, because this can be having the low priority. So instead of doing at the priority at the VLAN level, you will do at the group level, so that you are mapping the VLANs into groups. So instead of having 100 root bridges, you are having only 4 root bridges, because you are mapping the root bridge per group level, not at the individual VLAN level. Now you are solving the problem of using all the links, but at the group level, not at the VLAN level. So when you have large number of VLANs, it's important that you use the multi-spanning tree, because you are grouping them into you're mapping the VLANs into a single group, and you're applying priority at the group level.
So like how are we dividing the groups? Like are we setting any range for each group?
You can manually define what VLAN wants to go to what group, or you can put a range. It's up to you. You can manually call VLAN 1, VLAN 10, VLAN 25. You can randomly pick the numbers, or you can also do the range. It's up to it's up to an engineer how he want to define the root bridges.
Oh, thank you, sir. Sir, and also like I have a question. Like, so what if we have only 4 switches and like so it's difficult like to calculate the highest priority one, like where we do blocking stage, right? So 4 in a same distance. So how will it work?
No clarity. Can you please repeat?
No. See, let's say we have 4 switches where the distance is
So I
same.
have 4 switches. Yes, I took 4 switches. Okay.
Yeah, and the switches distance between the switches is same.
Okay, they're all counted in what fashion? Like square?
Yeah, square.
Okay, they're counted in square. Okay, so there is a loop here. Okay.
So there is a loop there.
Okay.
So how are we like blocking? How we will do the blocking here?
Well, this one will exchange the priority to this one and this one.
Yeah.
This will exchange the priority to this one and this one. So they all negotiate the priorities. Okay.
Yeah.
So this one, let's say this priority is 100, 200, 300, and 400.
400.
Okay. So which one will become the root bridge? This one will become the root bridge.
Root bridge.
So
Yeah.
forwarding state, forwarding state.
Mm-hmm.
The ports whichever is close to the root bridge will be in the forwarding state. So forwarding state, forwarding state.
Yeah.
Now either I can block this port or this port. Correct? Because
Yes.
this has highest priority. This is 400.
Yeah, yeah.
So either I can block this port or this port.
This port.
Okay.
Then how we will choose which port that we need to block?
So now I can do with 2 conditions. One is the port number. Let's say this port number is 1 and this port number is 2. The lowest port will be always in the forwarding state and highest port will be blocked. Okay, that is the default condition. If this port number is port number 1, this port number is port number 2, port number 1 will always be in the forwarding state. Okay, that is condition 1. If you don't want that, you can put a concept called cost. Okay, you can apply the cost. So whichever is the lower cost, let's say you apply the cost as 10 here and the cost as 100 here, you can block this one.
Okay.
So by default, the switch will always block the higher port. If you want to change that, you can manually apply the cost.
Okay, sir. I understood, sir.
Good question. Okay. Anyone else? Any questions? Okay. So we had seen spanning tree, port states of spanning tree, port types of spanning tree, per VLAN spanning tree, and multi-spanning tree, right? So the only one that is left is the rapid spanning tree. So rapid spanning tree is when switch is going through, let's say this switch and this switch and this switch, there are 3 switches again, and they are connected in the looped fashion. We talked about 5 states: discarding, listening, learning, forwarding, blocking. There are 5 states in the spanning tree, right? But there is a lot of time, like this switch has to send the BPDU, this switch has to send the BPDU, they all should agree. So this take 15 seconds, and this take 15 seconds, and this take another 5 seconds, this took another 5 seconds. So total like 40 seconds time is taking. So this is a big time to block one of the port, which is not good. Let's say you have a big network and you have somewhere loop in the network, and if it takes 40 seconds to remove that loop, there is like 40 seconds of outage in the network, which a multi-million-dollar company cannot accept that. If there is a 40 seconds outage, they might lose business. Maybe $10 million will be lost. So if the spanning tree is taking 40 seconds to converge, the end user will take at least 1 minute to 2 minutes for the MAC address to get broadcasted, sent out, reply coming back. It takes almost 1 minute to 2 minutes to get reconvergence. So this is not good enough for the spanning tree. So they reduced these timers by making the listening and learning at a time. So when this sends the BPDU, this will automatically listens. So they combine listening and learning into one state, which is called learning state again. So discarding state is same. It does not take any time because it is not participating in the spanning tree. That time is 0 seconds. Now listening and learning, they computed and changed that to 15 seconds. So it will send and listen the BPD at the same time. It's like a bidirectional communication. It does not send, wait for 15 seconds and wait for another 15 seconds to get the message back. Both of them will do at a time, so that the listening and learning can be collapsed into one state. So now they made 30 seconds to almost like close to equal to 20 seconds, because the forwarding and blocking will also be done at a similar time, because listening and learning is done on similar time. So this one will send the BPDU, this one will receive the BPDU at the same time. So they immediately put in the forwarding state or blocking state. So they convert that into the 5 seconds. So 15 plus total 5 seconds. So instead of having 40 seconds, they reduce that almost to 20 seconds. So that way, the rapid spanning tree will make the convergence faster by communicating faster between the switches, so that they collapse it, that the amount of time that it takes to put the port in the forwarding state or blocking state. So that is the help of the spanning tree, rapid spanning tree. Any questions?
Present, which one the many companies are using, sir? Rapid spanning tree.
Well, it depends on the use case, right? When you turn on the switch, it is by default spanning tree. But if you wanted to make any changes, for example, if your company has a lot of VLANs, you will use multi-spanning tree with the flavor of rapid. You can mix and match, right? You can also use like per VLAN spanning. If you have only like 10 VLANs, you don't have to do multi-spanning tree. You can put per VLAN spanning tree along with rapid.
Okay, when it is the more lands, we can use the rapid.
Multi. Because you have a lot of VLANs, you are putting them into groups, right? So you will use multi-spanning tree.
Okay, sir. Thank you.
I mean, honestly, if you take that route, people are trying to avoid spanning tree in the case. I don't want to confuse you more, but if you're talking about today what we use in the network, people don't even want to use spanning tree. They will use something like VPC, they will use something like ECMP, they use something like VXLAN, they use something like EVPN. There's a lot of different stuff that they use. But if you go to a hospital network, if you go to like an enterprise retail shop, they may not be using like advanced technologies, they will still use spanning tree. It depends on whom you're talking to. I mean, networking is something a small coffee shop needs and a multi-billion-dollar company like Facebook needs networking, right? Every small or big company needs networking. So it's really tough to tell which company, which is mostly used, because these are all concepts that are used according to your business needs.
And which is the most reliable one, sir? Like,
When you mean reliable, you mean to say what?
like the communication won't stop, or there won't be any loss of data or something.
There will be loss of data in any protocol, but the point is having a redundancy. Like if something goes down, how much fast we can fail over, how much fast we can have the convergence. That is what we are talking about. If you talk to someone in a Netflix data center, like if you're talking to someone who is working in Netflix, they might tell you that we don't even need spanning tree. It takes so much time to converge. We are using layer 3 everywhere. We are not even using layer 2. We are using like fast computing, ECMP kind of stuff. If you talk to someone like, maybe take a network like a small hospital, let's take a hospital clinic. You can take something like CVS stores. In that specific store, you might be using spanning tree because it's not that big network in the specific store. I'm just throwing out the names here, don't get me wrong, but I'm trying to say, if a store loses connectivity for 1 second, it might be a big deal, because your stores will lose the connectivity of what? Someone has to be on the line, and if they cannot pay with their credit card, their store will lose the access to the data center and they cannot make any purchases, right? So that is one kind of loss to the business. But if someone is like in a surgery room and they wanted to scan something in the surgery room, their PC is in somewhere, but their scanner is in the surgery room. If they lose the network, we are talking about losing a person's life.
Yeah.
So it honestly depends on how much critical convergence time that need to be less. Depends on that, we deploy the network.
Okay.
Yeah, I mean, it's a broad question, but I wanted to tell that there is no good answer for that, which is better than what. It depends on how much you want to spend. You can go on a flight with 24 hours time to India. You can go to a flight with 36 hours or 40 hours. Depends on what is your criteria.
Yeah.
Yeah. Okay, I'm gonna stop it there, guys. Any questions?
No, sir.
No, sir.
Sir, normally, how many pieces can a switch control, sir? It can handle?
Again, it's like a vague question, right? If you take a model switch, if you take 2960, it can go up to 48 ports. If you stack them, it can go up to 256 ports. If you take Nexus 9K, it can go up to like 68 ports. every switch make and model will be different. I'll take the same example. How many passengers a flight can handle? It depends on the flight size.
I got it.
I'm going to stop the recording there. I'm going to leave 5 minutes for any questions.